A mass m is attached to a thin rod of length L so that it can freely spin in a vertical circle with frequency f. What is the difference in the tensions in the rod when the mass is at the top and the bottom of the circle? So, if we draw what it looks like, let's say that this is the center of the circle that this mass will make. And let's say that this is the rod of length L. And this big dot represents the mass m, and it's spinning around it. And we need to figure out the difference in tensions in the rod when the mass is at the top and at the bottom. So let's draw some free body diagrams. So let's say that this is when it's at the top. Or sorry, when it's at the bottom. This is the tension at the bottom. And this is the force of gravity. So like when you think about it, when it's at the bottom, it's basically just hanging from the string, sort of. And over here, when they're both, when the mass is at the top, the force of gravity and the tension force both point down. This is because the ball needs some centripetal force to keep it from leaving this circle, just like to keep it from flinging the ball out. So this is the ball at the top, and this is the ball at the bottom, or the mass. And now we can write some equations. In this case, the positive x direction will be towards the center. So no matter where we are on the circle, the positive direction will always be towards the center of the circle. And that is what you should do for these sorts of rotational dynamics equations or problems. So from the first one, we can say that the tension at the bottom minus mg is equal to the mass times the centripetal acceleration, or the acceleration towards the center of the circle. And there's always this acceleration, as this acceleration or centripetal force is necessary to keep the mass from flying out in a trajectory tangent to the point on the circle. And then from the second free body diagram, we see that both of these are pointing towards the center. So when it's at the top, this is going to be like our center. So I'll just put a capital C to represent the center. So the center, when it's at the bottom, the center's up there, and when it's at the top, the center's down there. So both the tension force at the top and the force of gravity are pointing towards the center. And that is equal to the mass times the acceleration, centripetal acceleration. We can actually get rid of the subscripts if you want, because these two accelerations are the exact same, since it's on the same circle. And now to find the difference, all we need to do is simply just subtract these two equations. We're just simply basically subtracting these two equations from each other. So from here we get that the tension from at the bottom minus the tension at the top, and these are 2 minus mg's, so minus 2 mg is equal to 0. These two just simply cancel each other out. So from that we can move 2 mg over, and we get that the tension at the bottom minus the tension at the top is equal to 2 mg. And so that is the difference in tensions of the rod. And to see how much exactly, we can just simply move the tension at the top over, since the tension at the bottom is going to be greater than the tension at the top. And this would make sense, because at the bottom you would need a centripetal force that is pulling you back and keeping you in the circle, as well as the force of gravity that you will need to oppose to keep the mass from falling. And when you get to the top, the centripetal force is partly covered by the gravity. So at the top, the gravity kind of helps with the centripetal force. And that is how you would solve this problem here.